Hey everyone, we are back at it with the videos after a little bit of a break, and today we're learning about L'Hopital's rule. So starting off, let's talk about the name L'Hopital's rule. So there's two spellings. One, you get no P in it with a little hat on the O. The other one, it looks like La Hospital, but it's not pronounced La Hospital. It is pronounced L'Hopital. So please pronounce it correctly. And I know this doesn't tell you what L'Hopital is, does, or anything about it, but let's just start with being able to pronounce it. L'Hopital. Okay, so L'Hopital's rule is used when finding limits. Now, we didn't do this when we were doing limits earlier in the year because of the fact that we didn't know the calculus enough to do it. So here we are with lots of calculus under our belts, and we're going to learn about L'Hopital's rule. And I'm going to move the panda out of the way. So if you're finding a limit and you get 0 over 0 or infinity over infinity, it has to look like that, and you need to check first. You use L'Hopital's rule. And I know that still doesn't tell you what this is all about. So here's how it works. So you have something that looks like this. You have some function over another function, because obviously it has to be a sort of fraction-y thing to give you 0 over 0 or an infinity over infinity. But if you plug in your C value and you go, oh, look, I have 0 over 0 or infinity over infinity. What you do is you take the derivative of f of x and g of x, not using the quotient rule. It's just take the derivative of top, take the derivative of the bottom. And then you take the limit again, chucking that c value in. And it's possible you could get another 0 over 0 or an infinity over infinity. You would just repeat if needed. It's kind of like the shampoo bottles that say lather, rinse, repeat. Sometimes taking limits is like that. So let's take a look at a few examples. So I'm going to slide this up and put that here to cover it. So say we're looking at this guy where we have the limit as x approaches 4 of x squared minus 2x minus 8 over 2x squared minus 8x. Now, a lot of times when people know about L'Hopital, they actually go there first. But if you say plugged in x equals 3, you would just get some number on the top, a different number on the bottom, and you would have some number. So it's not an automatic thing to use L'Hopital's rule. You have to first check. So that's our first thing is let's throw the 4 in and see what happens. And I get 16 minus 8 over 2 times 16. So 32 minus 8 times 4 is 32. Yeah, that's a 0 over 0. This is L'Hopitalable or L'Hopitalatable. I don't know. Anyway, we can use L'Hopital on it. So we simply take the derivative of the top and the bottom. So we keep our limit notation. So limit as x approaches 4. And then the derivative of the top, I get 2x minus 2. Derivative of the bottom, I get 4x minus 8. So one thing to watch for on this, and this is a mistake that happens a lot, is that people will say that this limit is equal to 2x minus 2 over 4x minus 8 without the limit notation. These two aren't equal. The limits as x approaches 4 of these two things are equal, and that is all. So, and by the way, if you want to know the proof behind this, you can find that in our textbook. I'm not going there for the sake of time. Okay, so from this point, we can just plug in our 4 and plug in our 4 again. So I have 2 times 4 is 8 minus 2 divided by 4 times 4 is 16 minus 8. And I get 6 over 8 or 3/4. And there's my answer. So that is doing L'Hopital's rule. Now let's check this by looking at the graph. Now here is a case that an actual physical calculator does a better job of it. And I don't know if you can see it. It's kind of, I could have been zoomed in a little bit more. But looking at x equals 4 right there, you can see there's a little gap. Desmos and the iPhone app, or I don't know how the Android does on this, but they don't show the holes. But if I hit trace and put 4 in, I get a nothing there. But if I put something close to 4, like 4.001, I see 0.7499. Oh, that sounds like 3/4 to me. Or if I put 3.999 in, I have 0.75006. So I can check things and go, oh yeah, look, it worked out. So that is our first go at L'Hopital's rule. Okay, second example here. Slide this up, get something out of the way. And Okay, so looking at this guy, we have the limit as x approaches 0 of x squared over 3x minus 1. So starting out, do our normal check, throw the numbers in. So 0 squared is obviously 0. Cosine of 0, remember, equals 1. So we have 1 minus 1. So yes, this is a 0 over 0. It's L'Hopitalable. So we will keep our limit notation. Limit as x approaches 0 of, take the derivative. I have 2x over, and then remembering our chain rule and all that good stuff. So derivative of cosine is negative sine. And then derivative of the inside is a 3, so negative 3 sine 3x. And then minus the derivative of 1 is 0. And then we can plug 0 in, and in the numerator I get 0. And remember that sine of 0 is 0. Oh, well, shoot. So we go again. So this is the lather, rinse, repeat thing. So I simply just repeat the process. Keep my limit notation, because we are, y'all know by now that I'm strict about notation. So 2 over, and then we have the derivative of sine is cosine. Inside stays the same, times derivative of the inside. So I have this negative 3 from before. I'm just trying to like save a little step here, or not, I know. Maybe I shouldn't be, but I am. So I have a negative 9 cosine 3x, because that negative 3 from before, and then times derivative of the inside. So then putting 0 into this guy, I get 2 over, remember cosine of 0 is 1, then times 9, so I have negative 9. So this derivative is, or sorry, this guy is negative 2/9. Looking at the graph of this, maybe you can see it, maybe you can't, but there is a little, if I hit trace and look at 0, there's nothing there. But if I go 0.0001, I have negative 0.22222, and 2.2 repeating is 2/9. Or if I look at negative 0.001, same thing. So it's not a bad thing to check things and plug things in. But if you're asked to show, like to prove things, your calculator, me chucking numbers in it, that is not a proof. That is a verification. This guy is, doing it properly. Okay, so there's our first 2 examples. We're going to do a couple more, just because, sometimes you'll have x going to a finite number, but it's also possible you'll be going to infinity, and this is going to take a little bit of analysis. So starting out, so as x goes to infinity, I have a quadratic here, so that's going to infinity. And then 6x squared plus 11, that is also going to infinity. By the way, if this was infinity over like negative infinity, that would be totally fine as well. Okay, and you might be going, well, shoot, how could this go to anything that's real? So infinity over infinity, it can go to 0, it can go to infinity, it can go to any number in between. So let's find out what this does. So if I take the derivative of the top and the bottom, keep my limit notation, and then I have 10x minus 3 divided by 12x. That's gone. I started to keep going. It's like, nope, it's gone. And then, so I just have these 2 linear functions, and 10x minus 3, that goes to infinity. 12x goes to infinity. So if I repeat the process, take the derivative again, I get 10 over 12. So guess what my limit is? It's 10/12 or 5/6. So, and if you were to look at a graph of this, if you threw this into your calculator, and by the way, if you do throw things like this in your calculator, I don't have this in my calculator, but I do have the first example in. Make sure you put your numerator and denominator in parentheses as needed. Otherwise, the only thing that's getting divided would be the 8 being divided by the 2x squared. So be really careful with parentheses. Just something to watch for. So if you were to throw this guy in your calculator, then you would maybe look at the table and throw some large x values in. That would be the easiest way to do it. Just, go to your table and then just start typing some 9s. Lots of them. Okay, let's see what happens here. Now, there's 2 examples. We're going to kind of do them simultaneously because, as you can see, they're just reciprocals of each other. And you're probably like, well, so? Okay, so going to infinity again, linear goes to infinity. E to the x goes to infinity. So if we take the derivative of the top and the bottom, keeping our limit notation, I get 3 over e to the x. So if I take my limit, I get 3 over infinity. Okay, 3 divided by something really big. That's like saying, okay, we have 3 cookies divided by the population of the world. I know 7 billion is not infinity, but it is a pretty big number. You'd get no cookie, right? So if you see a finite number divided by an infinity, that is a 0. Okay, so what happens on the reciprocal? Because again, you know, this original problem, it is an infinity over infinity. It's the most sloppy infinity ever. And if I take my derivative of top and bottom again, it's the same as what I did before. I get e to the x over 3. So e to the x over 3, that goes to infinity divided by 3. Okay, take a really big number and divide it by 3. It's still a really big number. This guy is going off to infinity. So it's possible that you can get a finite number. It could be 0. It could be not 0 when you're going to infinity. If you ask me to, I could come up with a function that goes to any number you pick. Your favorite number, the number you hate the most, whatever. I could make it happen. I have superpowers. So speaking of superpowers, L'Hopital is one of my favorite things because it makes me feel like I have superpowers, because it's like this, it's such a nice, fast, slick way to find limits, and it makes me feel so smart. I don't know. So I hope you love L'Hopital's rule as much as I do. And I hope you also pronounce it as L'Hopital, not Le Hospital. So L'Hopital's rule is pretty dang cool.